Hi everyone and welcome back to Physics 2B. Today we are going to go over electromagnetic induction, AC currents, and electrical technology. So let's get started with the idea of electromagnetic induction. So this idea came from Michael Faraday, who was an English scientist, and Joseph Henry, an American scientist, and each of them independently demonstrated that you can produce a current using magnetic fields. So in the last section, we found that currents will produce a magnetic field. So these two scientists actually found that the exact opposite is true as well, that magnetic fields can produce currents. And this process of generating EMFs, or an electromagnetic motive force, and currents with magnetic fields is called magnetic induction. Now, I have here that it is also called induction, but we try to distinguish it from charging by induction in the electricity sake. So we will go ahead and call it magnetic induction. Okay. Now, today, currents induced by magnetic fields are very essential to the technology in our society. All right, so I'm going to talk about an induced EMF, again, electromotive force. So current is a result of an EMF that's induced by a changing magnetic field. So we have this simple apparatus that was created by Faraday, um, and it demonstrates that the magnetic field can produce a current. So we have a galvanometer, um, yeah, okay, I said that right. Um, and we have iron, which would be where the current is flowing and connected to a battery. So we have something that is generating our flow of current, our magnetic field, and therefore our flow of current. And we also have a couple of different um, ways of looking at this induced EMF, or what direction they will go in. So we have here, we have a coil, and that has some sort of current that is being induced by the motion of this bar magnet. Now, I will also look at a couple of other resources to use to understand this, because this can be a little bit confusing. But the main idea that I want you guys to get first is that this magnetic field, say from the bar magnet here, this is the bar magnet, um, will induce this current, okay, that's flowing along this coil. So in this first case, case A, we have a person holding that bar magnet, and they are moving it in the, we can say, upward direction, and it induces a current as so. Okay, and this can be thought of also with the right hand rule. We'll get into that a bit later, I believe. But the main idea here again is that we have the motion going up. Okay, so this would be like the velocity, and the current that is flowing now due to that motion. Okay, now let's look at the next one. The next one, the person moves the bar magnet downward. Okay, and we still have the same type of a magnetic field, but now the current is moving in the opposite direction. Okay, moving in the opposite direction. Now, if we switch the way you're positioning the bar magnet, so now it's no longer north is at the top, south is on the bottom. Now south is at the top, north is at the bottom. We do the same thing. We'll have a completely opposite effect. So again, the velocity moves in the upward direction. The magnetic field, I should label that B. The magnetic field is now going again towards the south pole of the magnet. And so now we have a current that looks like so. It's going towards the, actually that would be counterclockwise, okay? So we can continue with this velocity, again, south and north. We have our B field in the same direction as we had it in the last one. Difference here is that current, our current has now changed direction. So when you're going through these, it really takes some time for our brains to get used to it. And I've also, in the homework assignment, I have a part where you go to another resource called Hyperphysics, and it tells this to you again. So I think if you read it a few times, it'll start to make more sense, but I know that this is all new. It can be very kind of confusing at first to look at. Okay, so let me go ahead and just label all of those. Now we have a stationary magnet, so V is equal to 0, right? We don't have any sort of positive velocity, negative velocity, nothing's happening. It's just stationary, okay? And we do have a magnetic field, but we need to have some sort of motion happening, or else the current will be 0. Okay, so these are all the cases we could possibly have, and this will, like I said, take some practice. Okay, so keeping that stuff in mind, let's start to talk about magnetic flux. Now, this is the change in magnitude or direction of a magnetic field that produces an EMF. Okay, and experiments show a important quantity called this magnetic flux. So this is capital Phi is equal to magnetic field strength B times A, the area, and cosine of theta, where theta is going to be the angle at which the B field hits some area. Okay. So this is a depiction of this. We have some surface, okay, some surface area, A, and a magnetic field is hitting that at some angle that is, it's an angle between the perpendicular of the area, which it sounds really weird, but if you look at this, that's what it means, okay? So it would be B cosine theta would give you this value here, and that's what we're looking for, okay? So one other thing to note is the units, of course. The units of flux are going to be Tesla. Remember, this is Tesla. And then that is your meters squared. Okay, so your magnetic flux is in Tesla meter squared. One thing to, or an important note, I should say, is that any change in magnetic flux induces an EMF, which is defined to be electromagnetic induction. So a change in magnetic flux induces an EMF or some voltage change, okay? So let's look at that. We have EMF is equal to negative N, which is the number of turns in the number of loops, I should say, or turns in a coil or something like that. Typically, we're going to look at coils, times the change in magnetic flux, or this is what we just looked at, right? Magnetic flux divided by the change in time. Okay. Now notice this negative. This minus is telling us the EMF. The EMF creates a current I and magnetic field B that oppose the change in flux, and that is known as Lenz's law. So that is another law that is very important. So Faraday's law gave us this information, and Lenz's law told us why we have this negative value. Okay, so here is another depiction of what we were looking at earlier. So we have a coil, okay, and we have a magnetic field from a bar magnet. Again, let me just erase that. Our bar magnet here with some magnetic field B. And if we, how is it saying this? If we move our bar magnet toward the coil, then we will induce a current as so. Okay, and this is with the right-hand rule again, and this is going to be difficult to show without doing it in person, but if you can see this person's thumb, you have the right hand. It is pointing in the direction of the current, and the fingers are curling towards the B field here. Okay, so they're curling in that direction. Okay, then we have this one where we have a magnetic field and the bar magnet moving in this direction, so away from the coil. We'll have a magnetic field of the coil now and the induced current as so. Okay, so these are some of the rules that we saw before. Okay, and then this is if we switch our north and south poles. So notice our north and south poles have been switched. We have the velocity going towards the coil, and so we have an induced current pointing down now, okay, or going in this clockwise motion. Okay, again, this is going to take a bit of time to get used to. All right, so let's quickly look at an example. Calculate the magnitude, of the induced EMF when the magnet in this figure, which I forgot to attach, is thrust into the coil, given the following information. The single loop coil, so that means N is equal to 1, has a radius of 6 centimeters, and the average value of B cosine theta. This is given since the bar magnet's field is complex, increases from 0.05 Tesla to 0.25 Tesla in 0.10 seconds. Okay, so we are looking for the EMF, which I'm going to need to write down that equation. That is negative N, and this is going to be delta phi over delta t. Okay, now we need to remember what delta phi is, or phi. That is going to be BA cosine theta. BA cosine theta, which we were given B cosine theta. Okay. All right, so we have a coil with some radius. So an area would be, let's see, area of a circle is going to be pi r squared, right? This is in centimeters. We're going to need to convert that to meters. So we should have pi times r in meters. That would be 0.06 meters. Okay, so that would give us our area. All right, so now we have all of the components we need. Negative 1, since it's a single loop, times the change in phi. So we'd have the area stays the same, right? So we can just say A and then B cosine theta. That would be one of these first. Typically, remember when we have some change in something, let's say change in x, we say final minus initial. So this would be the initial, this would be the final. All right, so we'd have 0.250 Tesla minus A times 0.05 Tesla, okay, divided by our change in time, which is 0.10 seconds, okay? Let me calculate A real quick. That way we can plug it in. So that will be pi times 0.06 squared. So we get 0.0113. Oops. Meters squared. Okay. So we have that value times 0.25, there we go, minus that same answer times 0.05 divided by our time, which is 0.1, times 1. So our EMF, is equal to negative 0.023 approximately. And we can look back and see what our units are for EMF, and that is volts. So this will be in volts. Okay. All right, so I'm going to stop here and then we'll continue in the next video.